last lecture I gave, I told you a bit about what the fields in magnetic fields in sort of actual planets are. And in the second, I talked a bit about the results of simulations and showed you some movies and pictures of how the simulations work and what we're getting out of the simulations. And yesterday I talked a bit about what you might call the fundamental theory, the analytic theories of convection, and some of the sort of linear theories which help you understand what's going on. But I haven't actually talked at all about actually the dynamo mechanism produced in these simulations, and in particular how the tall thin column motions actually generate a dynamo, and what sort of dynamo they generate, and why they generate the dynamo they have. So this is basically a similar thing to actually I mentioned before. So we've got quite small length scales and a fairly time-dependent flow. Oh, I'll put this on here. Okay, yeah, fine, yes. That's good amplification there. So it's got strongly time dependent. If you remember, I showed you the movie of the rolls, and the rolls come and go. They don't last much more than a turn over time or two, each individual rolls. And the perpendicular length scale, that's the column thickness, is actually quite small. So there's some quite small length scales going on. But despite the fact that we've got quite a lot of turbulence in the sense of time dependence and small length scales, nevertheless, the dynamo-generated field is really quite strongly dipolar. Now, probably to somebody who's just sort of coming to the subject for the first time, that might not be a great surprise. I mean, after all, a lot of planetary dynamos are dipolar. People who've worked in dynamo theory for a long time are slightly more surprised by this, because in many cases you end up with quadrupolar modes, and not dipolar modes, and indeed in many linear dynamo calculations you often find quadrupoles and dipoles come in at quite similar values. An exception, of course, was taught by Anvar when he was thinking about his thin disks, but when you're talking about a spherical configuration, generally these two things will tend to come in close together. So that raises the question of why are we seeing these strongly dipolar modes actually preferred in planets. And really the thing I'm going to be talking about is why we see the dipolar mode strongly preferred in the simulations, because that's something I think I understand a little bit about now. Okay, so and another interesting question too, which again comes out of these things, is that we've got dynamos with only moderate or no rotation will often generate small-scale fields. That's the small-scale dynamo. But often have difficulty producing much large-scale fields. So plain layer dynamos typically produce quite small-scale fields, and it can be quite hard sometimes to get them to produce coherent large-scale dynamo fields. And certainly first attempts at producing solar dynamo models using the fully convective motions that have been pursued by Yuri Tumre and Sascha Brun have not really been terribly successful at reproducing solar-like fields. They typically tend to produce lots of small-scale stuff without much large-scale stuff. And so why is the rapidly rotating case rather strikingly different? And I think this is something which a lot of people have found. These dynamos in rapidly rotating systems seem to be much more coherent and in some sense much nicer than the non-rotating dynamos. So I'm going to talk a bit to the up. So that's basically the conclusions again. That's what I'm talking about. Back here. So here, that's just the same geometry picture that we had before, so I won't spend any time on that. It's the same thing as I showed yesterday. It's just to remind you of the basic geometry, so we haven't forgotten that. Okay, and now, again, I'll go through this rather rapidly, but it is important. These are the dimensionless equations of the model that we're actually using. We're in magnetic diffusion time now because we're doing full dynamo simulations. And recall that a strength of 1 unit of magnetic field is going to correspond to something about 14 Gauss, or 10 to the minus 4, 14 10 to the minus 4, of course, is the unit in Tesla. Okay, so here we've got the equation, that's the dimensional equation. Remember that it's going to be driven by the buoyancy forces here. We can also got compositional here and thermal there, viscous forces, Lorentz forces, and this very important Coriolis term here. Okay. So that's the dimensionless form, and remember we had the Ekman number and the magnetic Prandtl number coming in here. So remember the Ekman number is this quant ratio essentially of viscous forces to rotational forces, which, as I said, is extremely small in the core. The molecular value is that, and even on turbulent values, you still get an extremely low value of the Ekman number coming out. These simulations actually work on modified Rayleigh number. That's sort of like historical reasons that's the case. So it's rather than got the kappa nu on the bottom, it's got an omega kappa on the bottom, and that's the conventional Chandrasekhar Rayleigh number multiplied by the Ekman number. So it's different. So it tends to be not quite as big because it's the very large Rayleigh number multiplied by the very small Ekman number. So it tends to be something slightly more reasonable. Okay, and then we'll be using these Prandtl numbers. And in some of the simulations we'll be setting PM small, but most of the simulations I'm going to be talking about today, I've got PR is equal to PM equal to 1. So that's numerically the easiest thing to do, and the one which has been looked at historically most carefully. So where do we find dynamos in the parameter space, and what do they look like when we find them? Okay, so this is a set of results published by Kutzner and Christensen in 2002, and a lot of people have done these kind of calculations too, and since then found very similar pictures. So this is, I think, a fairly well-established picture. Okay, so what is the picture here? Right, so we've set the Prandtl number equal to 1, the ordinary Prandtl number equal to 1. The small Prandtl, the magnetic Prandtl number is sometimes called the Roberts number, Q, and was in this paper, but I'll talk in terms of PM as Jean-Francois did. So it's the same thing when PR is 1. S denotes dipolar dynamos, and R depicts non-dipolar, and I put reversing dynamos in a sense so that they reverse in the sense that the rather small dipole component sort of fluctuates around fairly randomly up here. So in that sense they are reversing, but they're not really reversing in the sense of the Earth, where you've got a large dipole field at one stage which stays there for a long time and then over a fairly short space of time reverses round to the opposite polarity. So they're not sort of classical reversing, not real Earth-like reversing dynamos, more actually like solar reversing dynamos typically is what you find up here. So we've fixed PR is 1, and these are 3 pictures of descending Ekman numbers. So 10 to the minus 3, 3 times 10 to the minus 4, 10 to the minus 4. So we're reducing the Ekman number as we go down from there to there to there. And this is a plot of the other 2 parameters. That's magnetic Prandtl number, or Q, and the Rayleigh number expressed as a ratio of RA over RA crit. So let's look at these pictures. So at 10 to the minus 3, what do we find? We find fairly moderate values of the Rayleigh number and fairly large values of PM, definitely PM above 1. We find a whole nice bunch of dynamos sitting up there, and they've all got S, and that denotes the fact that they're dipolar dynamos. So we've got a nice little region there of dipolar dynamos, and a higher Rayleigh number, where the Rossby number is not so small because the flow speeds are getting quite big here because the Rayleigh number is stirring up the fluid a lot. So over here the Rossby number is not so small, and inertial effects are also deemed to be important. Over here we find these rather chaotic reversing dynamos, which might be loosely thought of, I think, as small-scale dynamos, whereas these are clearly large-scale dynamos because they're very dipolar dominated. So then we moved, but one thing that was immediately noticed, of course, about this is that you can't go below a certain Prandtl number and a certain fixed Ekman number. So these are not low magnetic Prandtl number dynamos. This relates to the point that Jean-Francois was mentioning this morning, that there was some doubt for some time as to whether low Prandtl number dynamos really existed. Because certainly from this model, whatever your value of the Rayleigh number is, over here you won't find these nice dipolar dynamos below about Q is about 2. But then, what saves you is you increase the rotation. So basically, what you need to do is to make the rotation more and more rapid, so you're making the rotation more and more dominant. And if you do that, you discover then that the minimum Q for these dipolar dynamos starts to go down. And if you decrease the Ekman number even more, then that window opens up, and we're now getting down to values of the magnetic Prandtl number less than 1. And if you go further down than Kutzen and Christensen could do, because the computer technology has improved since 2002, so we're now down to almost down to 10 to the minus 6, and down to the 10 to the minus 6 we've done runs, and we can find dynamos with a Prandtl number of 0.1. So this thing goes, it appears that it gradually goes down and down and down as you decrease the Ekman number. So it seems clear that small Ekman number dynamos with a nice dipolar structure, small magnetic Prandtl number dynamos do exist, but the cost is that you have to go to very low Ekman number in order to see them. The other thing that's happening is that whereas these two regions were separated up here, by the time we've got down here, there's now a sort of boundary occurring here. So we still have the dipolar ones down here. There seems to be some kind of a critical Rayleigh number above which you start to get strongly inertial and reversing dynamos over here. And the suggestion, I think, which came, from Olsen and Christensen a few years ago, is that possibly in this region over here may be where the dynamo of the Earth actually sits. And it's certainly true that if you're in this sort of area, you'll be between these small-scale and the large-scale dynamos, and there you can sometimes get reversals occurring, which have sort of roughly Earth-like behaviour. So that sort of sums up how this thing behaves, essentially with its function of all the parameters, except the Prandtl number PR, and I won't go into that at the moment. Okay, this is the, relates to that previous picture. This is the kinetic to magnetic energy ratio in those dynamos. And here we're seeing the magnetic energy there, and this one, that's slightly weak there, is the kinetic energy. That's the L equals 1 magnetic energy, which is the dipole part. Remember that the L10, L equals 1, N equals 0 is the axial dipole component of the magnetic field when you decompose into spherical harmonics. So what's this telling us? This is telling us that where we're getting the chaotic small-scale dynamos, the kinetic energy is larger than the magnetic energy, and it's telling us that there's not much of a dipole either. The fraction of magnetic energy which is in the dipole mode is pretty miserable. But that as soon as you go from that regime to back to the strongly dipolar regime, as you'd imagine from the name, a lot of the substantial fraction of the energy is in the dipolar part, and the kinetic energy is now falling below the magnetic energy. So we're getting what something called the super-equipartition magnetic energies here, i.e. magnetic energies which are greater than the kinetic energies, which, as I explained, was what you expected in rapidly rotating dynamos. You can also look at possibilities of different heating mechanisms. So you can ask the question, suppose you have differential heating, or suppose you have internal heating, or suppose you have a model which is modelling compositional convection. You could ask yourself, whereabouts in the parameter space do you actually get dynamos occurring? And basically what you find, well, the main message from this is that internal heating is somewhat different. but all the others are only really sort of quantitatively different. So the picture is basically the same, whether you have here, we have a model for compositional convection, which consists of a fixed flux occurring at the inner core boundary, which is gradually being removed as the mixing occurs, so that nothing is coming out of the top. That's another version of the same thing with a slightly different chemical compositional boundary condition, it really is, from the one above, but not giving you significantly different results. There again is the S is this dipolar dominated regime, there's a critical Rayleigh number, and there's the reversing dynamo regime. So the only one which is really different from the various thermal boundary conditions is this one here, where if you put in a lot of heating, you can see that this dipolar region starts to disappear. So if you go up to a sort of 100% internal heating, then you won't actually find this nice dipole-dominated regime. So that's giving you one clue about the dipole-dominated regime. It likes to work when you've got differential heating, i.e. when the temperature gradient is biggest near the inner core boundary. That's closer to the inner core sphere. So that's telling us also that if we want to model this, to find nice dipolar dynamos and understand why they work, it's a good idea to look at differential heating cases, and so we'll focus our analytical approach on that when it comes up to that point. And I just included this series because this is one of the reversing dynamos, so this is one where you're in that borderline region. It's not a very low Ekman number dynamo. It's very difficult to find the reversing very low Ekman number dynamos for various reasons, because you end up having to go to critical Rayleigh numbers which are quite large to get to that boundary, and then it becomes very expensive computationally. And anyway, you have to integrate these things for a very long time to see significant reversals. You see this going great magnetic diffusion times, which is quite a long time. But there you can see the field there, 180-degree angle, and then it goes back, and then it comes back up and down. So you can see there are longish periods here where it's maintaining one sign, and typically the actual reversal time, just as in the Earth, is actually quite short. So it's actually taking only quite a short time to get from the top to the bottom, but once it's done that, it's staying there. So that is the sort of basic Earth-like picture of reversals that we have. I mentioned a bit, so these are the inertia, just to summarise what we've seen there from those results. Dynamos in the inertial regime, that's the R regime that I had there, where you're essentially in small scale stuff. Well, not only can quadrupolar modes refer to dipolar modes, but you can get even more bizarre things happening. You can get the convection can be localised in one particular area of the sphere. Sometimes it's localised in one hemisphere. Sometimes it's localised on one particular longitude. And it can even be localised in time. That is to say, the convection can actually occur in a burst of convection, and then a huge zonal flow is set up which suppresses that convection for quite a long time, so nothing happens and the field sort of decays away during that time, and then suddenly the zonal flow goes down sufficient to allow the convection to start up again. You get a huge burst of convective energy, drives up the dynamo, so the whole thing is actually effectively localised in time. So all these sort of things can happen when you've got strong zonal flows driven by the inertial forces after random stresses. That's where the inertial part of the dynamo is becoming very important. Okay, now the next thing I want to talk about is essentially the cartoon picture of how dynamo action actually occurs in these rotating columns. So this is essentially the equivalent of the Parker picture, which I'm sure you're familiar with, and also equivalent to some of the pictures that Jean-Francois was drawing this morning for his von Karman dynamos. So basically what we're going to do here is use the nature of rapidly rotating convection, which we discussed last time, which is based on linear theory and based on simulations, to essentially draw a sort of cartoon picture of the field generation process. And we'll see also that this links into the alpha effect process that Karl-Heinz Raedler discussed gosh, at the beginning of last week, which seems a long time ago now, and we'll see that as he pointed out, the helicity u dot zeta plays a key role. So zeta is going to be the vector of vorticity in what follows. I don't use omega anymore because I get confused with my frequency omega. So that's why I use it there. So remember this picture, okay, this is one I've shown before here. These are the columns of vorticity, and remember they're not real roll-like columns, they're more sort of spiralling structures which go in and out and in and out, like so. But the main point of these things is that they're pretty well Z-independent, very Z-independent, and that as E gets smaller, the columns get thinner. Okay, so that's the cartoon. Right, so let's see what we've got in this cartoon. So this is the equatorial plane here, okay, and that's the Z direction, so that's parallel to the rotation axis. And what I've drawn here is a whole lot of convective columns. And you'll notice straight off that the picture is only a cartoon because I've drawn these roll-like circulations, rather like Busse drew roll-like circulations, as nice round circles, because that's easy, but they're not really round circles at all. They're actually much more elliptical structures, and not only are they elliptical, but they're actually spiraling out, as we saw in the last picture. But I'm going to ignore all that and just draw the fact that it goes round and round, so that you get a circular picture here and here. So what's the red arrows denote what you might call the primary flow, which is the thing which is convecting the heat out, which is the motion of the rolls themselves. So the rolls are going round and round like that in a fairly Z-independent way, and they're going to be hotter on one side here, yeah, and cooler there, so that the buoyancy pushes it out, and the cold fluid then pushes it down. So the buoyancy is actually what's turning these things round. Okay, and they turn round the same way in an entire column, because the vorticity is more or less constant all the way from top to bottom in these calculations. Okay, so that's the primary circulation. So that's an anticyclone. Now, these pictures, you've got to get used to how you look at these pictures. This is supposed to be in front of you, the front, and that's the back. So this one here is going round in this direction, i.e. it's going round clockwise if you look at it from above, which is the negative direction in mathematics. So that corresponds to westward flow there. And this is cyclonic motion, which is going round eastwards if you look at it from above. So it's coming out in front, going back there. So that's going in the same direction as the rotation. So in a little cyclone, remember that the flow is going round, it's rotating slightly faster than the rotating frame of the mantle. So there it's rotating slightly faster, there it's rotating slightly slower. Okay, and so these are the anticyclones, these are the cyclones, and of course we get one after the other as we go along in phi. So this is the phi direction here, that coordinate there is the phi, angular phi direction. Now the blue is the secondary circulation. So the blue corresponds to the fact that every time that you have a roll going around like that, you also have some vertical flow. And I've drawn the arrows this way because this is actually the way they actually go in the numerical experiments. And we'll come back to the direction of where these blue arrows are relative to the red arrows, because that's very important later on. But the simple picture I have is the one where you've got lots of helicity, because you've got lots of motion around like that, and you've got lots of motion up and down like that, so the fluid is screwing around as it screwing that way, isn't it? In that one, and screwing that way and that one. Okay, so those are the secondary flows that are moving up and down. That's the Z flow, the UZ. These are, of course, the horizontal components of the velocity, which are associated with vertical vorticity here. And the symmetry is such that there's no Z motion up here, so that in these anticyclones, the flow goes upwards in the northern hemisphere and downwards in the southern hemisphere. And for the anticyclone, and for the cyclones, it does the opposite.
So why is that the equatorial plane?
This is the equatorial plane here, yeah? I've just cut that, yes, yep. So there's a roll, yep. So this is where the roll pokes out, yep, at the top, yeah, of the sphere, yeah, yeah. And this is where the roll pokes down on the bottom boundary, yeah. So the equatorial plane is halfway up, yeah.
But the label is somewhere else.
Oh, sorry. Yeah, yeah. Sorry, yes, the label should be down there. I'm sorry about that. I know that's yeah. that's just to do with the typesetting, I think. Yeah.
Chris, what's the ratio of blue to red?
Velocities?
Yeah.
They're comparable. They're comparable. Remember I asked you that question about if you remember. You can always see that they're going to be comparable because if you think of the boundary, if the boundary is, say, at about 45 degrees, yeah, then it's the component of velocity which is in that direction, which is 0. So at the boundary, the component of velocity in the s direction and the z direction has got to be pretty much comparable. And that's determined at the boundary, and then that goes more or less right down through the whole thing. So in these asymptotic work and in the actual thing, the vertical velocity is always comparable to the horizontal velocity. So we're in the same situation as you've cunningly constructed in your experiment. Okay. Now, we'll need to know about how the magnetic field works, but this picture is sort of quite important. This tells you a bit about the azimuthal field. So the first thing to notice is that the azimuthal field, this is the azimuthal average of B phi. First thing to note is that it's positive up here and it's negative there. It's antisymmetric. So it's the symmetry which is rather important here. And it's pretty well 0 on the equator, so it's plus up here and it's going to be minus down there. And this is the plus B phi, and that's minus. Blue is more sort of purple, it's come out here. It means minus, and this means plus. And that configuration, that way round, is associated with when BZ, the field is positive near the inner core boundary. So I haven't plotted BZ there, but if I had plotted BZ, it would be looking like that. And that means you have a red thing on the top here, where the patch where the BZ comes out. You have a blue bit down here, so that would correspond to a dipole in the positive sense. Okay, so this is the kind of B phis we're actually going to get. Okay. Right, now remembering what the cartoon of the flow is, hopefully, you've got that in your mind, and remembering also what the nature of B phi is, we can now start thinking of the mechanism for generating Bz from B phi. Now remember, this is the tricky bit of the dynamo cycle. This corresponds to the alpha of the alpha-omega cycle, if you're going to have an alpha-omega dynamo. As you see, we're not, but nevertheless, this is the bit that generates the poloidal field, the Bz, from the toroidal bit, the B phi. Okay, so those of you who are sort of interested in solar dynamos will know, of course, that the big B phis are generated by the differential rotation, and the tricky bit is always how you get the poloidal field, and you need some kind of an alpha effect to do that. And this is what happens in this particular model. So here we've got phi is in that direction, and z is in that direction. This is supposed to be in the northern hemisphere. This picture is a sort of slice in the northern hemisphere, where B phi is positive. If you remember, so you've got to think, let's see, you've got to think of B phi positive, so we've got some slice somewhere in here is what we're talking about. Like that. And that is supposed to be, the green thing there is a magnetic field line of B phi, and I've drawn it in a positive phi direction because with arrows in that direction, because B phi is positive up in the northern hemisphere. So what does all that flow actually do to you? Well, it does two things. The first thing is that there was the secondary flow, that's the flow pumping up and down, that's the UZ flow, and that goes down and then up. It went down in the cyclones, it went up in the anticyclones, down in the cyclones, up in the anticyclones. So it stretches that B phi out into a wiggle, and of course here you've generated positive Bz, and here you've generated negative Bz, and here positive Bz, and so on and so forth. So of course that process has not generated any mean BZ at all anywhere, because you've got just as much positive as negative. So at that stage you haven't actually achieved anything very much. But then you've got to think now as to what happens to that in the S-phi plane. So in the S-phi plane we now have velocities, those column of motions, turning it round, remember, so that inside here we're bringing out hot fluid will be brought out there, and cold fluid will be returning back there. So these are the things which are being turned around by the buoyancy. And what is this going to do to the magnetic field? Well, that BZ positive is going to be shunted up in this direction here by this field, and down here the negative BZ is going to be shunted down there, positive BZ up there, so that in net we're going to get positive BZ created here and negative BZ created out there. Still haven't created any real mean field yet, but you've managed to separate out BZ positive and negative parts. So the net effect is to create positive BZ inside and negative BZ outside, and that's exactly the same as actually happens in that dipolar field. If you remember, I said that the positive B phi was correlated with the dipole where you went up near the inner core boundary and come down as the dipolar field comes down and closes outside. Okay, now, so that's the standard sort of, it's essentially a Parker-type picture, but it's been translated into the particular configuration that we actually have inside these simulations, and hopefully also inside the Earth's core. Well, of course, there are a couple of things to remember about this. Why does this picture seem to work? Well, I'll just say a few things about that now. This is basically a low RM picture. Now, why do I say that's a low RM picture? I say this is a low RM picture because when that BZ was generated as positive there, I said it was pushed up there. If, of course, I was at really high RM, it wouldn't just stay there, it would go round and round and round and round. It would be moved round and round, and only would it predominantly end up there if there was a short correlation time associated with that, i.e. if that flow suddenly switched off after it had got from there to there, then that would be fine. But the correlation time is not that short in these dynamos, so that's not really what's working. That would actually take this thing right round into unfavourable and wrong places if we allowed this thing to actually advect around a large distance. What is actually happening here is that the magnetic Reynolds number is not that large, even the global magnetic Reynolds number is not that large, and when it's acting over these rather short length scales of the roll distance, it's actually a moderately small RM, so that it never gets the opportunity to get pushed further in there because it's controlled by diffusion. So this diffusion is a rather crucial part of this whole process. It's the thing which stops the twisting going on and on, and the twisting going on and on is the bad news. That's what averages out that averages out the magnetic field and ends you up getting a rather poor mean field. So that's why this thing works rather nicely. We're in what Karl Heinz, I think, in the very first lecture described as the first order smoothing approximation, or the SOCA, the second order correlation approximation, he called it. Those are two names essentially for the same thing, and the crucial thing about this limit is that the small magnetic Reynolds number for the small scale flows means that you're essentially balancing the advection of field directly by the diffusion, and the non-linearity bits never come into it. Okay, so now the usual way for solar dynamo people, this will look a bit odd, because the way you generate B phi from BZ in the solar dynamo is by differential rotation. And it was thought for some time that that was also what was happening in these dynamos, but actually it turns out, when you look at it carefully, it isn't. Now, again, I've go down. I'm going to have to put you in a bit more darkness, I'm afraid.
Slide. Put slide. You see a slide?
Yeah. I'll just go down to slide. Yeah. Yeah. So I think if I put it down a bit, I think you'll. Hopefully that picture hasn't come out like Jean-Francois's picture hasn't come out terribly well. But nevertheless, I think it's good enough, actually. Here's a BZ here, there. So we're now in the Z direction there, the phi direction here. So what are we looking at here? We're looking at a line of BZ being moved out by the secondary flow here, because the secondary flow, remember, comes down from there in the, it goes up in the anticyclones there and down in the cyclones. And we're now at the equator here, the equatorial region here, and the UZ has got to vanish there, so these things have got to return back around there. So the return flow has got to take that one along like so, and this flow line has got to go around back out like that. So the fact that the flow lines are lined up with the cyclones and the anticyclones produces a picture like that. So that the BZ is now drawn out, and here we've got a B phi which is positive, and there we've got a B phi which is negative, and here we've got B phi positive, and so on. So again, they alternate in direction along there and there. And then we look at what the primary flow does that in the SZ plane. And up here, if I'm looking in the northern hemisphere, I'll just concentrate on that one, which is between the anticyclone and the cyclone. So there I'm there. And so the positive is being swept down there. So that's where the B phi is going to be positive. Out here in the northern hemisphere, it's going up like that. So that the negative up here, so the negative B phi between this anticyclone and cyclone, that's going to get negative B phi up there. So you get negative B phi there, positive B phi there, and so that is actually what you want for actually to get the signs right. So that produces the correct, flow. So that's the S goes down here in this picture, so that's close to the inner core boundary. So the inner core boundary are generating positive B phi in the northern hemisphere, which exactly corresponds to the picture we had before. So if you just go back to that picture, yes, there's the positive B phi being created by that process. So all the signs work out correctly, and so this is essentially what you'll recognise as an alpha squared mechanism. So this is essentially an alpha squared dynamo, and of course there will be some differential rotation and stretching out of magnetic field. But it looks very much in these particular dynamo simulations where in the region where these dipolar fields are being produced, that the differential rotation is not very big and it's not doing as much as this. So this seems to be the important mechanism in these dipolar type solutions.
You mean the stretching by the solar? I mean the differential rotation, because it's slowly faster.
The differential rotation does not do very much, mainly because the magnetic field essentially locks everything together in the module, so there isn't very much differential rotation. So
the zonal flows, they don't.
Yeah, that's it. There's zonal flows. There's not very much zonal flow either. So that in these models, the contribution to magnetic field generation from zonal flow actually appears to be less than the contribution from this mechanism here. Okay. And that's sort of why we're getting alpha squared. And of course alpha squared tends to give you steady dipolar fields, so that's sort of consistent with that. Okay. So in a sense that's perhaps the main difference between this sort of geodynamo model and the solar dynamo alpha omegas, where alpha omegas typically give you reversing fields and migrating dynamo waves. 11-year cycles, which we don't see, of course, in the Earth. So the explanation as to why we're seeing long periods of similar polarity here is basically down to the fact that this is an alpha squared dynamo rather than an alpha omega dynamo. So that's sort of fairly fundamental. Okay. Right. So So this can be thought of essentially as a macroscopic alpha effect. So my U prime and B prime, those are the velocities that are associated with the small non-axisymmetric rolls, the convection rolls, so the U prime, and that B prime there is the B prime that was actually being produced by the individual roll process. So that's I'm thinking my U primes and B primes as what's happening on the scale of the individual rolls, and I'm thinking of the bar as being the azimuthal average, so the average over all the rolls. Because all the U primes are all organised in the same way all around the rolls, and because the UZ and the U the vorticity all correlated in more or less the same way in every single roll, then these things all add up together. So it is really a mean field dynamo in the sense that all the small scale contributions from each roll are adding together and giving us a large scale field when averaged over the azimuthal direction. When you start to look at the maths and write down all the equations, you begin to see that your cartoon picture is rather simplified. The picture I described actually only describes one of the two terms of the electromotive force. That picture all relates to that term there. There's another term there. But that doesn't really make too much difference, because if you go back and have a look at the sort of effect of that, you can see that it adds up to the effect of that. So it all makes a consistent story. The fact that we've sort of omitted a few of the terms here doesn't really change the whole overall picture. So that positive B5 is BZ is created near the ICB, and of course when you get into the steady state, the positive BZ that's been created by this has got to balance against the large scale diffusion. So that's what it is. When that balance is established, that determines what the magnetic field strength is actually going to be. And again, just to emphasize here that this all works because the Rn based on the roll width is not too large, so we're in this nice first order smoothing approximation limit where we know that it all works nicely. Yeah, this is a slight digression here, but I think it sort of fits in here. It's often noticed that anticyclones are actually stronger than cyclones in this, so that although in that nice little cartoon picture I drew, I had everything sort of similar, the anticyclones and the cyclones both comparable, actually the anticyclones are somewhat stronger than the cyclones. And if that's the case, then you've just got to do a Stokes theorem integral around it, and of course that tells you that there must be net circulation, so that tells you that the westward flow has got to be near the CMB, and there's got to be eastward flow near the ICB. So a mere fact that there's a preponderance of anticyclones over cyclones immediately tells you from Stokes' theorem that the field is going to drift westward, and it does in most of these simulations. You can ask yourself the question, the more difficult question, or why are the anticyclones stronger than the cyclones? I've got a little, let's go back to the cartoon, that would probably be best. Yeah. We go back to this one. What happens if to BZ from a flow like that? Well, near the equator, BZ is going to be vectored in here and vectored in there, so you can see that BZ is going to be concentrated in the anticyclones, and BZ is going to be weaker in the cyclones, so the magnetic field itself will have a periodic behaviour, being BZ stronger there, BZ weaker there. If you work out what happens to B phi, it's just the opposite. You get B phi stronger in the cyclones and B phi weaker in the anticyclones. And basically, if we now go back to this one here, so the B phi here is the opposite behaviour, so that's strongest near the cyclones and weaker near the anticyclones. And the B phi is the one where the magnetic damping is the strongest, so the cyclones are more strongly damped than the anticyclones. The cyclones are more strongly damped than the anticyclones, And that's why the anticyclones end up being stronger than the cyclones. So it should say anticyclone there, sorry. And that gives you the observed cyclone-anticyclone asymmetry. So basically it's the B5 field which seems to be damping the cyclones more strongly than the anticyclones, and thus ending up with a westward drift. Okay, westward drift was known to Edmund Halley in 1600 and something, so it goes back quite a long time, that observation. Okay, yeah, well, of course, where does all this go wrong? Well, when the columns start to break down, of course, you can get reversals and so on. So the large RA, the columnar structure and the generating the dipolar field breaks down. So this nice tidy picture of all the flows going up and down in this nice coherent fashion starts to break down. And then the dynamo becomes more of a small-scale dynamo than a large-scale dynamo. And the idea basically here is that when it's in its small-scale phases, it digs away at the dipole field and reverses it. So that's one idea. There was another idea which I had some time ago with Graham Sarson, which is that thin boundary layers are developed at large RA, and then basically you could get a breakdown of the boundary layer, and that could produce a perturbation which might be large enough to disrupt the dynamo, which I still think is quite a nice idea. Although it must be admitted, it hasn't been followed up much with more elaborate simulations as yet. It's just never got around to doing it. Okay, just a quick refresher of what some of the things I said yesterday. Remember that the horizontal wave numbers are much larger, derivatives are much larger, so the scale of variation is large in the phi direction. We're now looking at the case where the convection onset's close to the tangent cylinder, rather than the case I focused on last time, which was the internal heating, because the tangent cylinder convection is the one that corresponds best to the theory, and we saw that it was in differential heating cases where you get the strongest dipolar behaviour. So that's where I'm looking at for my theory. And because of the S structure, the variation S is large, but it's not quite as large as it is in the phi direction. So there's a slight asymmetry between the length scales in the S direction and the phi direction for the convection onsets close to the tangent cylinder. But both of them are still very large compared to the Z dependence, which of course, as always, is weak. So we've got Cullinan convection still here. And you write U in terms of that, UZ, and then the round and round horizontal motion leads to Z vorticity. And those are the same magnitude as we discussed. The UZ and the US are the same magnitude. But that means that U phi is some tiny bit smaller, which doesn't really make much difference in practice, but is sort of asymptotically convenient when we're coming to discuss the actual mechanism, so that we can actually make that one small compared to the other, which is a slight simplification in the theory. Okay, so I mentioned that the magnetic field is doing things to these columns, so let's think now exactly what the magnetic field is actually doing. So now I'm thinking about the back reactions. I'm now thinking of the problem of how does the magnetic field actually affect these columns, these columnar structures? What is it going to do? Well, the way to start the thinking about it is to think about the Z vorticity equation, because that's obviously an important equation, because we've got these columns going. So let's think about what's balancing in the Z vorticity. Well, perhaps we'll start with that. That's the buoyancy term there. That's the one that's actually driving the convection. So that's the forcing term for this. So that's driving these rolls around. What exactly balances that? Well, partly there's this term here. That's the viscous force there. So that's the viscous damping. So you're buoyantly driving it. You've got the viscous friction, which is stopping it. There's a time-dependent term there, because then that's out of phase, because it's an I omega, so there's a wave-like motion going on as well. Over here, we've got what you might think of as magnetic damping. So I'm putting the effect of a B phi in here. So I'm typically expecting that B phi is going to be the most important component of the magnetic field or acting on these columns, because it goes straight through them transverse to the column direction. So that is also a damping term, so that sort of does the same sort of thing as this term here. It damps the column and has to be balanced by the driving of the buoyancy force. And then we've got the joker in the pack here, which is T2. This is the Coriolis term. This is really comes from the vortex stretching. Okay, so that means that if you have fluid which is, if there's some stretching going on, so it's going upwards in one direction and downwards lower down, that's stretching out the column, so that can also produce vorticity there. So that's another thing which is coming into the vorticity balance. And that's going to be fairly crucial in the discussion that comes up next. Okay, well here, lambda is just the L-SAS number, that's the dimensionless measure of the strength of the magnetic field, which is sort of a number of order 1 in the Earth's core. So that just tells you that this sort of term is going to be comparable to the other terms in this balance. Well, it's actually going to be probably more important in this term, but because we've got high derivatives in the linear theory, they're equally important. Okay. So that's just the physics of that. So the system is completed by a z velocity equation and a temperature equation, and z velocity equation also has a B phi. So we've got this system of equations, which is quite complicated, but nevertheless, I mean, they can be solved quite easily mathematically, and then close it off with boundary conditions, and that's the correct boundary conditions to apply. Right, now of course what we're interested in is the helicity in the model, so what the output of this calculation is going to be is the u dot zeta, and we saw from the little cartoon that we're expecting lots of zeta, positive in, one sign in the northern hemisphere and the opposite sign in the southern hemisphere. You put in the expression in terms of w and psi, and that's what you get out. And it's actually got this rather nice simple form. The contributions from uz omega z, which is the one I focused on, is actually the same as the contribution from us omega s, which I haven't really talked about, but that's of course there as well when you do the full calculation. Zeta s us, that's there when you do the full calculation, and actually these two terms are more or less equal, and they give you a mean part of helicity averaged around in the azimuthal direction. Now, of course, the B phi you're going to get is going to be quite different if you've got a dipolar field from a quadrupolar field. A dipolar B phi is going to be positive up here, it's going to be negative down there, it's going to be naught at the equator. A quadrupolar B phi is maximum at the equator and goes down to 0, or small values as you move away from the equator. And I've got two little simple models. There we've got the z h squared minus z squared, so z equals naught gives you naught, so it's got the dipolar symmetry. This one's got quadrupolar symmetry, so it's maximum at z equals naught, and it goes down. In fact, this one actually goes to 0 at the top, so to make a nice simple model. Okay. Now let's look at the helicity patterns that we get out, and this is really fairly crucial. This is the helicity pattern you get out, the helicity distribution you get out when there's no magnetic field. This is when you've got the dipolar magnetic field, and the strength of the dipolar magnetic field is roughly the sort of magnitude that we actually see in the simulation. So that's the choice of the strength of the magnetic field is to make it comparable to the one you see in the simulations. And the green line here is the helicity, and I'll talk about this one first. Well, the most striking thing is that there is an absolutely huge difference between these two pictures. The helicity here is, well, there is some helicity, and it's got the right parity. It's positive in the north, it's negative in the northern hemisphere, it's positive in the southern hemisphere. But look how small the maximum is compared to the maximum up there. And that's with a realistic magnetic field and realistic values for the wave numbers and so on. So this is all yeah, so there really is this huge disparity in the helicity with magnetic field and the helicity without magnetic field. Right, now let's think, obviously when you see that you've got to think, what's doing that? I mean, why is that happening? What's producing this? And if you actually look at the vorticity and the velocity, you can begin to see what's actually going on. The vorticity is fairly uniform. If you remember in Emmanuel Dormy's pictures, it looked pretty uniform as it went up and down, and when you do the sort of exact calculations, you find that it is. So there's not much variation in omega z as you go right from the bottom to the top of these columns. So omega z is, or zeta z I should say, is pretty constant. And it is when you've got a magnetic, it's slightly less constant when you've got a magnetic field, but to a first approximation we can think of this as being essentially constant. The huge difference is in the vertical velocity. There's quite a bit of vertical velocity. That's the imaginary part of the vertical velocity. There's quite a lot of vertical velocity when there's no magnetic field, but it's all imaginary. The real part is this curve here, which just lies underneath that green line there. That's the real part of the velocity. On the other hand, over here, when you've got magnetic field, then you've got a really big size real part of the vertical velocity, and you also got quite a big imaginary part, but the crucial difference, the reason why this green thing has become much bigger, is because you've got now this much larger vertical velocity. So it's the vertical velocity which is absolutely crucial in this picture. Now let's just pop back right to our cartoon, and then we can see what's actually happening. If I just pop back to the cartoon, this cartoon here. Now, I just drew a map cartoon. I drew my UZ in phase with my vorticity. So I drew those arrows nice and up, right through the middle of that thing, and I drew that arrow down right through the middle of that thing. When there's no magnetic field, that picture is wrong. What is actually happening is that blue arrow is actually occurring there, and the down arrow is actually occurring there. It's actually occurring there. So the vertical velocity is out of phase with the vertical vorticity. You average and you get sine times the cos, and that averages to nothing. Okay, what you've got to have is sine times the sine, and that gives you a sine squared, and that averages to something. So what is actually basically happening is that when there's no magnetic field, remarkably the helicity is really quite small because the phase is wrong between the flow in the columns and the flow up and down the columns and the columns themselves, the vortices themselves. You can sort of think about why that should be, actually. It's a lot of it's actually in the non-magnetic case. A lot of it is actually driven by the boundary, and at the boundary, the UZ is going down where the US is coming out, and the US is largest there and there. So the UZ at the top boundary is naturally largest up there, and the opposite sign up there. So that naturally, from the geometry of this thing, you get the thing is out of phase. So that's the first thing. And then you think about, well, what about the buoyancy forces? Well, the buoyancy forces also produce a vertical motion because there's a component of gravity in the vertical, but the hot fluid is also here and the cold fluid is there. So again, the Z component acting on the buoyancy, fine, but it's out of phase. So it's not actually giving you the in-phase component that you really want. The only thing which is really giving you an in-phase bit is the Ekman suction. Now, this is a bit of theory I haven't covered, and you'll just have to take it on trust. But when you have a rotating fluid hitting a boundary, it produces a velocity. It sucks fluid actually into the boundary, and then it moves it around and spits it out. That flow is in phase with the vorticity. So the vertical flow due to the Ekman suction, if you've got a no-slip boundary, if you've got a stress-free boundary, you don't have any Ekman suction, but if you've got a no-slip boundary, then you will get motion which is in phase, so you will get a small contribution which is in phase, which is why you get a small amount of helicity. You don't get a zero helicity. If you remember the picture I actually showed you, it's not naught, but it's pretty small. So, right, so now we've got to why the, let's just flip through this again. Let's go right through this one. Back to where we were. Yeah, to this picture here. So now we've sort of understood why this one gives only a rather feeble helicity because of the phasing relationships. So why does this one do much, much better with the magnetic field? And I'll come back to that in a minute. I've just got to show you one more picture, well, two panels here. The quadrupolar field is here, and the quadrupolar field is sort of intermediate between the dipolar. It's nothing like the huge helicity that we got from the dipolar field, but it's somewhat bigger than it was if you got no magnetic field at all. So a quadrupolar field certainly helps the helicity, but not very much. And this one over here is where you got Ekman suction. This is less obvious what it's doing, but it's actually pushing it off the zero because the suction is actually there. So there's actually quite a region here where you're getting net helicity. So although it doesn't look much different at first sight from the stress-free one, which we had before, there is actually considerably more net helicity around this sort of area where it's quite important. Okay. So now let's try and understand why it is that that dipole field is producing this massive increase in the helicity. Well, I'm just going to sort of drastically simplify my equations. I'm going to just look at the real part. The imaginary part should be there, of course, but the wave speed is quite small, and the omega turns out to be quite small. So that to a first approximation, we can just look at the real part of the Z vorticity equation. That tells you basically the story. So there, the real part then has this balance between buoyancy driving, viscous damping, magnetic damping, and vortex stretching. And this is the picture which is basically correct, provided you've got more or less constant vorticity all the way along the line. Okay, so UZ is north of the equator. We said that the real part of UZ is driven at the boundary, but it's actually quite small compared with what happens when you've got magnetic field there. So the Z integral of that thing is basically fairly small. So if you integrate that over Z, you've basically got something fairly small there, and you're finding out that the average, the driving has got to balance the sum of the two dissipations. Now, with quadrupolar fields, that gives you no problem, because this is sort of more or less big where that is big, and that balances that, so that you end up with a duz by dz, which is small pretty well everywhere. But with a dipolar field, it's rather different. With a dipolar field, these two terms are located in very different regions. Near the equator, that's 0, so everything's got to be balanced by the viscous dissipation. Further up, this thing comes in a big way, where this is a strong effect, so there this thing becomes positive. Near the equator, it's basically negative, so it's changing a lot, so that means the UZ you get out by integrating that equation is large. So vortex stretching has to occur to compensate for the fact that the damping is occurring in a different place from the driving. So it's the damping and driving occurring in a different place which is leading to vortex stretching, which is generating the helicity. So that's producing this flow along the lines, and this is all an in-phase thing. This is all in phase with the vertical velocity. That produces a UZ, which is in phase with the vertical vorticity, the right phase relationship that we actually want. So that actually explains that picture. Okay. Now, so now we've got the fact that dipolar fields and quadrupolar fields affect the helicity in very, very different ways. And this, of course, is going to give us a preference for one type over the other, and it's easy to see we're going to get a preference for dipole fields, because the dipole field was the one that had loads of helicity. And so we've got loads more helicity there for a dipole field, so the whole thing is much easier to sustain if you've got a dipole field. So this is something which actually produces a difference between dipoles and quadrupoles. And there was some previous work, a couple of years ago now I guess, which was by Cardan and Nathaniel Schaefer. They looked at dynamo action in the roll kind of configuration, just like I've got here, but it was driven by shear rather than driven by buoyancy. They made the assumption, which is quite a reasonable one for their configuration, that UZ was just proportional to Z. And when they did that, they found that quadrupolar modes, in fact, were preferred. So that even in these roll-type configurations, you can get polar modes if you don't have this business about the helicity affecting the magnetic field affecting the helicity. There's the no dynamo. You increase the control parameter. It was the Prandtl number here. You pushed it up. And the thing that I just want to draw attention to is that these are all squares at the bottom, and the squares are the quadrupoles, and the round of the dipoles. So the first modes to onset in their dynamo are the quadrupolar modes. So if you don't have this helicity effect, that's actually what happens. Okay, now I'll just finish off by describing some simulation. So that's all the theory. So how well would all that theory actually work out when we actually start to do some simulations? Does it actually bear out? Well, see, it bears out more or less, but there are, as ever, when you actually do some simulations, you find other things which you didn't actually think about. Yeah.
Is the net thing that the Earth's dynamo is subcritical dynamo?
I think that's quite likely, yeah. I mean, remember that we know that the Martian dynamo suddenly collapsed, and that suggests something that came down like that and then fell off a loop, yeah? I mean, the classic subcritical behaviour is you're up here and you go down there, and oh dear, it all drops to zero. So that fits there. More particular, as we'll see, most of these dynamos are subcritical, and that's what I'm going to talk about now, actually. So subcriticality is exactly what you'd expect here, because if the helicity is driven by a magnetic field, when the magnetic field's there, the dynamo will work perfectly well, but switch the magnetic field off, and it will never be able to get back up again, because the helicity is going to be knocked out, and so you won't be able to recover from that. And that's exactly what happens here. So this is a set of runs at E is 10 to the minus 4, PR at PM is 1, stress-free boundary conditions. Stress-free because that gives you the best chance, because then you've knocked out the Ekman suction, which the Ekman suction can drive dynamo action even in the absence of magnetic field. So that knocks that out, so that gives us the clearest indication of the situation. So here are a load of dynamos runs, and let me explain them. So number 1 has got Rayleigh number 400, and it was started from a large solution. That's basically started from the benchmark dynamo solution. So it was started from a large solution, and it just happily goes on forever. So that's that one there, which has been run for 2 diffusion now, which actually run for a lot more than that, this one. But it just goes on forever, and it's a dipole-dominated solution. I just quickly... Yeah, that's the picture. That's what you actually get. So it's highly dipolar, as you can see. That's the 400 one, yeah. And it's got the red at the top and the blue at the bottom, and the azimuthal average magnetic field has got the B phi positive there and the B phi negative there, just as we had it in the cartoon picture. So that's all okay at RA equals 400. The second one is RA equals 600, which is a stronger dipole solution, so it's much the same as the 400 one, but its amplitude is a bit bigger because you're kicking it a bit harder, so the field strength is a bit higher. Number 3 is also 600, so these are 3 and 2 are exactly the same parameters, The only thing that's different is the initial conditions. This was started off with a strong field initial condition, again, basically from this one actually. Whereas 3 was an initial small seed field. It's this thing down here. So it started off with a small field of 10 to the minus 6. But at 600 it did grow, and it grew, but eventually it ended up actually as a relatively weak quadrupolar solution. So it didn't actually even end up as a proper dynamo, as a proper dipolar dynamo. Now 4 was that, again, we like that with a different one, so with a different initial field, but basically this same kind of thing happened. And at 500, a small initial seed field decayed away. So this one here, at 500, it actually decayed away. And at 550, a small field just gently grows. It takes a very long time, but it did actually eventually grow. But it again ended up as a quadrupolar field. So what is this all this telling you? It's telling you that the critical for onset of dynamo action, that's kinematic dynamo action with no magnetic field there, is somewhere between 500 and 550. But at 400, you can get a nice, strong dipolar solution, bombing away quite happily, and it never decays. So that you're getting dynamo action at 400, coherent, nice dipole fields, even though you have to go right up to 500 before you actually get the kinematic dynamo to grow. So you're somewhere on about here. This is the, so in this picture there, that must be at about 500, between 500 and 540, and I've got a nice dipolar dynamo down there at 400. If I go down there, it eventually falls off that loop and the thing will actually collapse, and it collapses about 360, I think, for that one.
So that is growth rate versus...
So no, this is amplitude. This is actually amplitude. This is field strength up there against Rayleigh number along there. You know, so that's the strength of the driving. Yeah.
But even that, you need a minimum Rayleigh number.
Yeah, that's the Rayleigh number you need to get critical. Yes, that's where this part with this thing will actually come back. So when you've got subcritical behaviour, you know what happens. It's always unstable down there. It comes up like that. It comes up like that, doesn't it? Actually, back down there. Of course, the pictures. If you're plotting B rather than mod B, it's always symmetrical about that line there. So it comes out of there, but this is always unstable, so you never see it. That's the critical there, and that's where you get the stable dynamos, dipolar dynamos.
Tracing the simulation at the point where you jump to the high field branch.
This one?
No.
Yeah, this one.
Yes, that where you jump up there.
Yeah.
How much field you generate?
Not when you jump up. You never end up on that. You end up on something which is considerably smaller. You can sort of see it actually if you look at the 600 one, which actually this is actually a plot of the magnetic energy there. And although it's got a lot of orders of magnitude here, if you look at the 600 one from the initial C field, it ends up more or less on the same line as the 400 one did, and considerably less than the 600 one did. So if that's the 400, so that's about 500 there. So there's the 600 one here. So if you start up here and from the small seed field, it will grow, but it doesn't grow up to there. It grows up to something which you've got an amplitude about there, which is about the same as the amplitude of the 400 one there, and considerably less than the amplitude of the 600 one up there. So this sort of the thing that actually grows off the kinematic is actually different from this dipolar dynamo. You don't actually ever get to that dipolar dynamo in that way.
And you seem to be jumping from branch to branch as you reduce.
That's right.
And that's what is being observed in the telegreen as well. You jump to a lower thing and then you jump one to a U, a velocity field, which will be totally different than the one you captured right.
Oh, I didn't know that. That's interesting. Okay, so I've already discussed that nice, simple dipolar picture. So I think I've got a picture some here. Yeah, these are the pictures that you get. So that's the 600 one here. So that's the stronger field branch, still totally dipolar dominated. But whenever you increase the Rayleigh number, you tend to get more small-scale structures coming in. So it's not quite as perfect a dipole as the previous one, still much more dipolar than the real Earth, I might add. And this is what happened to the one that came up from here. Yeah, it started off with mostly a small dipolar perturbation, not completely dipolar, so it sort of stayed dipolar, but eventually it went into a quadrupolar. But it's a bit of a mess, really. So I mean, that's the final state of this one up here. Yeah. Okay. I don't want to do it for time, but I'll do a few more minutes. Yeah. Right.
So all such subcritical dynamos discussed also for Sun?
No, don't think so. No, I've never seen that. No.
I think the accretion-less dynamos, the MRI dynamos, they of course are perfect examples of what should really be a subcritical one.
Yeah.
But the Sun, we believe, is driven by convection. I mean, if it's
Yeah.
driven predominantly by magnetic buoyancy, then it might be a different story, but this is not.
Okay.
Yeah, I mean,
The Lorentz force is the important thing.
yeah, I mean, really, I mean, we should have been doing this. I mean, I'm always saying this. I mean, we should have done this years ago because I mean, it's been. You know, there's this thing called the benchmark dynamo, where we all sort of got this particular model, and we all tried to use our different codes to get the same answer. So a lot of people were working on this, so we know this thing really worked. And in order to get to the benchmark dynamo, you have to be told what magnetic field to put in as your initial condition. If some poor bloke doesn't know about this and tries to integrate from a small seed field, they never get there. And it sort of became widely known in the community that this was correct, because otherwise you never got the right answer. But really the consequence of that, which we should have been thinking about that a bit more. Okay, so this is reducing Ekman number, the same basic story. Left is the evolution of magnetic energy from a small seed field state. On the right are the large, what happens with large fields starts. So that, now what do we see here? So the critical for onset of instability, that's this point here, is now between 1 and 2, which is between 530 and 500, so it's somewhere between 500 and 530 is the onset of kinematic dynamo action. But this black one up here is at 400, so it's, again, this is quite subcritical. And then if you push it down to 385, then it stays on for, I mean, this is a very long time, these are diffusion times here. So it's actually, although it doesn't look very long, it's actually quite a long time that it's stayed up. It's nearly half a diffusion time it's stayed up. And then it fell off. So that means that we've actually just got sort of down here. I should say that there's some interesting picture. I mean, this picture that I've just drawn here is the classical picture for hysteresis loop, of course. But that, of course, assumes that you've got a steady state. Of course, what we've got here is a turbulent velocity, because the fluid velocity is coming and going all the time. But it's not immediately apparent, actually, exactly how this curve works in such a circumstance. I mean, you've got there's some interesting dynamical systems issues, is what I'm trying to say here. Presumably, as you go along here, I imagine what happens is that there comes a point at which it will eventually decay, it will eventually drop off this thing after a very long time. Presumably there's some value of the rate number for which you're completely safe, for which this thing integrates on forever. Then there'll be a value just below that, which after a very, very long time it will eventually just drop off. And then as you go further and further down here, the drop-off time will get shorter and shorter. That's what I imagine happens. I imagine that there is a specific value here at which the thing finally drops off. But exactly how that's... There's a limiting process there. You're approaching critical and there's this very long time scale. And how that actually works out, I don't really know. But anyway, that's another interesting problem for one of the students to sort out. Okay. Growth of magnetic field at low, yeah, now we've got round down to 10 to the minus 5. I mean, we were a bit worried that maybe this all happened because our dynamos weren't at low enough Ekman number. We wanted to establish that it wasn't just a medium Ekman number result, but it doesn't seem to be. I mean, seems to be asymptotic. So again, what have we got here? Between 480 and 540 is linear critical. At 460, comfortably below that, we've got persistent magnetic fields. And then again, you find that eventually, if you push this down over here, the field actually doesn't stay up, it starts to collapse. The nature of the solutions, these are some of the lower E solutions. So again, it's basically dipolar and basically columnar structure. So those are pictures similar to the ones I've been talking about before. So these are what the columns actually look like in the real thing, as opposed to these nice idealised linear models and cartoons that I've been drawing. But nevertheless, I mean, it seems that the cartoon does a reasonably good job. But there is a bit more to this story. This is the plot of the helicity. Now, this is in the Z-plane, and you can't take the equator as the Z-plane because the helicity is 0 on the Z-plane because it's symmetric. So you have to take a Z-plane, a cut-in Z-plane which is slightly above the equator, and I've taken it at 0.5. You can see how far you are. It's just sufficient to cut through the top of the inner core. So if you imagine that inner core sphere, and you take a slice like that, if it was a little bit higher, you'd miss the inner core altogether, but we're just hitting the inner core, and there's a little tiny ring there, which is just the tightness, sort of cut the top of the egg off there. So that's where the inner core is, but that's where the tangent cylinder is, so that if you draw the cylinder, the imaginary cylinder that goes round throughout the inner core, you get to that. What are these two pictures? This one is the helicity when there's a magnetic field. That's the strong field solution helicity. And that's the zero field or weak field solution, i.e. negligible field when the field is not doing anything. And you can see, you can see that this one is red and blue and red and blue and red and blue and red and blue. So you can see why it's got a sort of average which is really rather small. And it's exactly in agreement with that picture, cartoon picture I had of the phasing being wrong between the vertical velocity and the vertical vorticity. Whereas this one here is a lot more patchy, the helicity, but it's basically all the same sign. So what there is, it's all adding up together. Interestingly, I think the scales are not that different, but it's the phasing which is completely different. So that's the thing which seems to be making the difference. But there's a bit more to it than that, as we discovered. As I mentioned, when you do the simulations, you find out that there are additional effects going on which you hadn't thought of. And this is a clue to one of them. This is the radial velocity with the field, and that's the radial velocity without the field. So notice that the convection has got stuck to the tangent cylinder. That is to say, it came on first near the tangent cylinder. That's where linear theory predicts it. But as you increase the radial number, you'd rather expect this convection to move out throughout the whole fluid, because at higher critical radial numbers, you'd expect it to be unstable everywhere. But it's not doing that. But with the magnetic field, it does do that. Now, why is that? Why is the convection occurring everywhere in the sphere with magnetic field, and not everywhere in the sphere when you've got no magnetic field? So, I mean, the helicity picture is, of course, consistent with that, because we saw the positive and negatives all lined up with there, so that's where the helicity was, is where the convection was. But why is that doing there? I think the answer is in this picture here, which is the differential rotation picture. So this is the azimuthal velocity of the strong and the weak field solutions. So this is the weak field's azimuthal flow, and that's the strong field azimuthal flow. That's an equatorial section, and the crucial thing that this one's got that one hasn't got is that this has got a huge amount of differential rotations, loads and loads of eastward flow, westward flow there, and it's eastward flow there. With no magnetic field, that's what you get. The zonal flows drive the Reynolds stress drive a pattern like that. And so there's a lot of shear here. So what is the shear actually doing here? Well, the shear is not helping the dynamo. I mean, this differential rotation is not actually driving the dynamo. This one has got has a You have to go to higher rate numbers to get this thing to work rather than this one. So this is not helping the dynamo at all, and it's not helping the dynamo because it's shearing off the convection. So it's this which is actually confining the convection close to the tangent cylinder. So the differential rotation is having a totally negative effect on the dynamo here. Because it's trying to be an alpha squared dynamo, it just doesn't, this differential rotation is only just suppressing convection and doing, as I said, doing negative things to it. Whereas in this case here, there is quite a lot of zonal flow, because, and it's mostly magnetically and thermally driven, I think, but there isn't the big differential rotation that's going on in this particular thing here, and that's why the convection can survive here, and it's not surviving there. Okay, nearly finished actually. Oh, thinner columns at smaller e. Okay, so that's comparing 5 times 10 to the minus 5 with a 10 to the minus 5 one there. So where you're getting the columns, the picture is a bit messy, but you can see that where you get the columns there, they are much, much thinner. So you're seeing, as we said, that's consistent with the asymptotic theory, and the scaling of going down to smaller scales seems to happen despite the magnetic field, as I mentioned before. Okay. Oh yeah, this is no slip boundaries. This is just one I've just been doing very recently because I wanted to compare what happened with no slip boundaries, because there you've got the Ekman effect. And again, you still find a bit of subcriticality, but the depth of subcriticality is much less. That is to say, the depth of subcriticality is the distance between there and there. And now this thing has moved right back down to there. So it's still just subcritical. At 360, the field is maintained. And at 360, it's not actually a kinematic dynamo, but it's between 390 and 360 is the growth. And if you go below 360 down to 340, the field collapses. So this thing here is now come down to a fairly narrow bit. So we're still getting some subcriticality, but less in the no-slip boundary condition case. Partly it's due to the additional Ekman suction, which produces helicity even if you've got no magnetic field. I think probably a bigger effect is the fact that the no-slip boundaries on the outside are also bad news for the differential rotation. The zonal flow is cut down by the no-slip boundary. So if you're making sure that U phi is 0 on the boundary, the outer boundary, the core mantle boundary, then that doesn't give much opportunity for much differential rotation. Of course, that doesn't happen on the Sun, because on the Sun you've got stress-free on the outer boundary, but on the core mantle boundary, if there's a rigid boundary condition there, then of course you're cutting down that differential rotation. So that cuts down the differential rotation, and so then again, so the velocity field opens up, and this enables you to get more helicity out here. And when you get this non-linear stuff coming out here, the phase sort of shifts a bit from that basic linear picture, and although you don't get quite as much, you actually get quite a lot of mean helicity occurring in that picture too. So there's still more red and blue there, and it's still slightly dominated by blue there, but it's becoming a bit less clear-cut in this thing. So it's clear that the azimuthal velocity plays an important role in this story. And if you do things which cut down the azimuthal flow or make it more homogeneous, make it less shear, less differential rotation, then that in this kind of dynamo is bad news for the dynamo. So the shear is almost always negative for the dynamo in these kind of situations. So that's interesting because, of course, as is known, shear can often promote dynamo action in other circumstances. But if the dynamo is coming out of this kind of alpha squared mechanism, then that's how it's actually operating, then it doesn't like that shear. You might eventually get totally different kinds of dynamo branches coming in, probably with a totally different mechanism, but that's not what's actually happening in this part of the parameter space. Okay, so that's shows you, I think that's pretty well all. So that's the helicity there. So again, so no slip helicity. It's actually, the magnitude is somewhat down here, but there is nevertheless quite a bit of coherent helicity there. Otherwise, not get much as that. Okay, so some conclusions from all this. There are two broad regions in dynamos: the strongly dipolar dynamos, which are very stable, and there's the inertial dynamos, where inertia is important, and there will be a more chaotic field and more small scale. Dynamos are of alpha squared type, and the generation mechanism, I think, is now reasonably well understood. The helicity production is strongly influenced by this dipole magnetic field, and this leads to subcriticality. And a preference for dipoles over quadrupoles. Oh, I should say, I mean, this is not, a lot of this is not me. I make this clear. I mean, the mechanism was sorted out, I think, primarily by Peter Olsen, but also with Uli Christensen's help. This I had a bit to do with, but other people have also had a lot to do with that too. Helicity production stronger in the case of magnetic field. There was a paper by Fritz Busser in 1970-something, I think it was, which sort of got forgotten, as these things often do. But nevertheless, he pointed out there that magnetic field could aid helicity production in plain layer dynamo models. So again, that's not really completely new, although the spherical stuff is new. And there's this important point about the differential rotation, which is of course a very non-linear effect and therefore somewhat harder to analyse, but is nevertheless clearly suppressing convection and helicity, promoting supercriticality. So that's another part of the story. Okay, I think that's my time. Yes, thank you.
Thanks, Chris. Thanks for bringing us closer to below our feet.
Yeah.
And questions, please.
Come on.
Yeah, I just wondered whether you could just repeat the argument which you gave about how the Lorentz force, the magnetic field, you promote helicity.
Yeah.
Just went a bit faster.
Yeah. Yeah. It's sort of, it's the equation. It's really this equation, I think, which is the crucial equation. This is the vorticity equation, the vertical vorticity equation. Okay, and this says that vorticity is produced by buoyancy. Okay, so why does vertical vorticity arise in the first place? It's because the hot fluid is moving out, yes, the cold fluid is moving in, so that on each individual column you've got a torque, yes? So there's basically a torque produced by the buoyancy force, and that's what's producing that's the main vorticity production source. Yes? So that's
the Coriolis force then.
Well, no, it's not the Coriolis force, it's the buoyancy force, isn't it? It's the curl of the buoyancy force, but it's basically the buoyancy. Whenever you've got convection, it produces whenever you've got convection, if you have hot fluid rising and cold fluid falling, that is producing a net torque, so that is producing vorticity in that direction. Sign vorticity in that direction. So if you've got hot fluid coming out from the inner core boundary out to the core mantle boundary, that's pushing it that way. Cold fluid coming down from the core mantle boundary down to the inner core boundary that way, that's producing vertical vorticity. Yeah? It's just it's the buoyancy force, and it's the curl of the buoyancy force. This is the difference of the buoyancy forces across the line. So you're pushing one way and pulling the other, so that's a torque producing vorticity. Yeah?
Up to a geometrical factor. It will have
sure. Up to
cosine,
yes. In your language, it's grad P cross grad lambda. Yeah, in the thing you put up this morning. Yes. Right. So that's this term here. Okay. Now, what's stopping that thing going faster and faster and faster? Well, it was the viscous force. Yeah. But there's also the magnetic friction, because if you try to roll around like that, and you've got a magnetic field threading through that roll, it twists it up, yeah? Doesn't like being twisted up, the Lorentz force opposes that. So, and it always acts essentially as a friction on the roll. Whichever way round the roll is going, it twists it up in that particular way, and therefore it's I like to do magnetic friction. It's of course anisotropic, because it's not like ordinary viscous, it's depending on the field direction, but here it's simple because the field is going straight through the perpendicular to the roll axis. So that's that term and this term. Okay, so there's this term, and this term. Yeah. And then there's the vortex stretching. Now that's vortex stretching. There's planetary vorticity there because the Earth's rotating all the time. Yes. So if you stretch a column fluid, you're generating vorticity by intensifying the rotation. And if you're doing the opposite, if you're contracting, then you're reducing the vorticity due to the rotation. Okay, so that's vortex stretching. Now, if these things were locally in balance everywhere, yeah, if the buoyancy balanced the friction everywhere, yeah, then there'd be no need for this term here. Yeah, you could have that term very, very small. Yes, right. Okay, got that. Yeah. So if the balance is local, i.e. at each point the buoyancy force is exactly equal to the magnetic friction plus the viscosity, then there's no need for any duz by dz term. But that's not what happens with a dipole field. Because with a dipole field, this thing is 0 in some places, and it's very big in other places. Yeah? So it's impossible for this to balance at every single height. Yeah? That can't balance at every single height. It's got to balance overall. Yeah? So overall, integrated over the whole thing, the buoyancy's got to balance the two friction forces. But this one will be the friction will be much bigger where the field is, yeah, so that'll be over-damped, yeah, and so that will require stretching to occur there to compensate. Yeah, because at that point where the huge field is going around, the damping will be massive there, so that you'd end up with too small a vertical vorticity unless you compensate by stretching there. So there's got to be stretching there. There's got to be contraction at the other places where the buoyancy is too big and there's not enough damping to balance it, so that therefore you've got to have duz by dz varying along that column. Integrate that up and you end up with a great big uz. So that's why you get a uz. So the crucial thing really is where does the damping occur and where does the driving occur? They all occur, it's the same, yeah, then you don't need any du by dz. You just end up with a simple column. Just all goes round. But if that's not the case, then the vortex stretching has to come in, and so you end up with this these big UZs and the big Lisp production. Okay? Yeah, thanks.
Very impressive.
Well, it's like,
Any other questions?
You mentioned differential rotation connection with the inner. So what's that actually in connection with the inner core spinning up or down, rather? Or where does the differential rotation come from?
The differential rotation. Yeah, well, the differential rotation, when you've got no magnetic field, yeah, the differential rotation essentially comes from the zonal flows. If you remember, these things always spiral in a particular direction. So these things always spiral out.
Yeah, right.
And that means that the integral of us u theta or us u phi is non-zero. Yeah. So so therefore that's essentially what you need in order to generate a differential rotation. Because of the way this thing spirals in the non-magnetic case, that always produces a differential rotation which is eastward. It's faster at the outside and slower at the inside, which is like the sun, if you think about it. I mean, if the sun was columnar, well, we know it isn't, but I mean, just think if the sun was columnar, then faster at the outside would correspond to a faster equator, and slower at the inside
Yes.
would correspond to slower poles, which is exactly what the sun does. And I mean, I think most people think that that is basically what is actually, that mechanism is actually what's creating the solar differential rotation. I mean,
Yes.
I know it's not, of course, in columns, but nevertheless, I mean, that's what's producing, that's why it's going faster at the
In that
equator.
connection, we would use the lambda effect language, and such a lambda effect
it's the same.
would be generated if the turbulent motions were mostly horizontal rather than vertical.
Well, again,
Maybe
you can write down the Reynolds stress as a small set of perturbations, and do an average, and that's exactly the same. Essentially, it's exactly the same as what I'm saying there. I mean, if you actually look at the kind of motions you want to get, then you'll find that they all have to be slanted. I mean, what they mustn't be is coming straight out and in. If they're all coming straight out and in, then the average of the US U theta all averages to 0, and you don't get any effect. So the crucial thing is that these things have to spiral. Once they do that, then you're going to end up with differential rotation. And if you want to get rid of the differential rotation, you've got to have some other effect that's stopping. It could be boundary friction, as we saw in the no-slip boundaries, or in the stress-free boundaries, it could be magnetic field, all tending to lock it all together again. But there's got to be something that's going to oppose that.
Okay, anything else? If that's not the case, then two announcements. First, you see in the background the plan for the rest of today and tomorrow. And then on Thursday, the day after tomorrow, we'll have a school dinner. That will be here in the third floor, outside, or in fact, this one room or something. Our secretaries will prepare it, so that will be after the student presentations. So that will be like at 6 o'clock roughly. 6:30. Good news, yeah? Yes, I think so too. So, here we have then the lectures. So, the student presentations. The student presentations, so be prepared and check out that your laptop works. We have first Fred Gent, supernova driven turbulence. We have then Dario Passos, a low order dynamo model. Helen Popova, the effect of meridional circulation on the dynamo. And Andrew Bagley reconnecting flux rope dynamo. Tomorrow, we have done a slight swap in the schedule. Matthias Reinhardt, who will be giving a presentation on the test field method, which goes beyond the standard test field method and is a new nonlinear test field method. That will be not given at 9 o'clock. That's too early for him. He sleeps normally at that time still. So he is giving the talk instead at 2 o'clock. And then Petri was happy enough to speed up his final. Whoops.
Well, that's my power.
Oh, sorry.
No, that's okay. So Petri was happy enough to speed up his final preparation of the talk so that we can all hear him speaking then at 9 o'clock. And then François again, as usual, at 11 o'clock. Any questions? So then you have coffee. We will convene here at 4 o'clock. Computers simultaneously.